Okay, in this video, we're just going to really kind of explore these reactions, the SN1 and SN2 in particular. We're going to talk a little bit about the history of how people have looked at the mechanisms of these reactions and the history of the chemists that did it. We're going to take a look at why iodide can enhance rates of SN2 reactions with other nucleophiles. And then we're going to take a little detour to talk about chemical weapons and how they actually led to the development of the first synthetic chemotherapy drugs. Okay, so it's important to remember that the stuff we learned in textbooks was not handed down to us on stone plates from a mountain. It was stuff that we had to kind of work out ourselves, mostly by ruling things out. So for instance, for the SN2 reaction, we essentially knew early on that it seemed to go with inversion. This was first found by Walden, so sometimes it's called a Walden inversion. But usually, since the reaction was different, since the reactant was different than the product, we were kind of comparing apples to oranges. So here in this example, 2-bromooctane gives us 2-octanol. The optical rotation goes from -34 to +10. Is that scientists doing that didn't understand if that was a full inversion, what 2-octanol was supposed to be. Once in a while, you'd actually see SN2 where the direction of the rotation doesn't change, but that's just because there was no way to link the configuration of the carbon with the rotation. So they're kind of flying blind. So Hughes et al. In the 30s had this great idea. So now to make sure we're comparing apples to apples, let's just have our starting material and our product be the same thing, right? So in that case, we know that if they're opposite configurations, they should have equal and opposite optical rotations. How are we going to follow the reaction if the product is the same as the starting material? Well, they're going to use radioactive iodide. And every time that radioactive iodide kind of displaces one of our normal iodides, we'll be able to follow incorporation of radioactive material in our product, essentially with a Geiger counter. Okay, so we're going to be able to follow two different things in this reaction. We can follow how radioactive the product is, which is the same as the starting material, so how radioactive the octane is, and we can measure the optical rotation of the whole system. So again, as we set it up, here's what it looks like. So we're starting with essentially pure R iodooctane, 100% enantiomeric excess, no racemization, and no, which is to say the optical rotation is measured to be its maximum, and no radioactive iodooctane yet. Okay, so I found this GIF. Let's run it. Okay, so as the reaction starts, we're going to see racemization and isotope exchange happen. And what you're going to see is the percent racemization is always double the isotope exchange, right? Because every time I flip one from R to S, I make a racemic pair of an R and S. So halfway through, now we have exchanged half of our red normal iodide with our radioactive iodide, and we've made a completely racemic mixture. And if you follow the rates of those reactions, and they did, they saw that the rate of racemization was exactly twice the rate of isotope exchange. So this is a pretty elegant experiment, elegant meaning simple and gives us a lot of good stuff. It's an elegant experiment that shows us that yes, the SN2 reaction always results in inversion of stereochemistry. But we still kind of need to do some experiments to rule out other possibilities. So for instance, we usually, in the modern day, we think about SN2 reactions as needing backside attack in the transition state, and we think of the SN1 reaction as requiring a planar carbocation, right? And we know that because we understand the hybridization of cations. But could it be possible to have front side attack like you see here? or even attack on the ligand itself? Or is it possible to form a non-planar cation? So can I imagine like an SN2 reaction that actually keeps its stereochemistry because the cation is never flat? Well, there's a couple of different questions, and a really amazing paper in 1939 set out to answer them both. And this was one of the first times in sort of in the field's history that somebody made a molecule in the lab specifically to answer a mechanistic question. Right? This is at kind of the birth of synthetic chemistry overall. And so this was kind of an amazing watershed paper described in the 70s by another sort of titan in the field. 1939, Bartlett and Knox published an account of their work on this thing. Fantastically influential paper, shaped the interest and viewpoint of many chemists about what we call physical organic. Physical organic is really people that care about the mechanism and how these things happen. And again, the more we know about how they happen, the more we can improve them, and the more we can do. Okay, so this is a hugely influential paper, really elegant, super duper clever. All right, so they made this compound. This is a chloride. It's kind of the two-dimensional paper figure is presented here. The kind of ball and stick thing is to the left. You can kind of see it's not quite a chair. It's kind of like a boat on the bottom there, and then you've got a bridge on top and two methyls hanging off that bridge. Okay, so you can kind of picture it here. We can make it a stick figure, see it a little bit easier. Okay, so why did this compound get made to answer these questions? Well, think of the SN2 reaction. I can't do an SN2 reaction on this molecule because I really can't get backside to that chloride leaving group. It's too crowded, right? And so A, I can't get backside, and B, how would an inversion product of this even look, right? I can't have some nucleophile like pointing in the middle of this strained, crowded ring system. That just doesn't work. And so there's no way I can do backside attack, and even if I could, there's no way I could actually have a stable inversion product, just because of the geometry and the ring strain involved in the system. So if attack happened at all, it'd have to be that weird front side thing that we drew earlier. Also, if it lost the chloride by an SN1 type mechanism, we'd expect this flat carbocation that's kind of sketched here. And if I do that, my angles are messed up. This is really, really strained, much more strained than we could sort of possibly have. And so it's hard to say that that's possible either. So if we did form a cation, it would have to be one of these, weird non-planar cations like I drew earlier. So this is the cool setup. We've made a molecule that seems like it can't do SN2 as we understand it, and seems like it can't do SN1 as we understand it, even though it's a sp3 chloride. Okay, so we're going to test this reaction. They're going to pretty much put it in really, really forcing hardcore SN2 and SN1 conditions, and they're going to see if they see any products. Another thing we can think about is, what about elimination? Is that going to mess us up? Actually, it's not. If you remember E2, the E2 reaction needs that proton to be anti-periplanar to the leaving group, right? And these blue hydrogens that are there, they're not anti-periplanar like they need to be. They're actually gauche, right? They form a 60-degree dihedral angle, and so I can't get that double bond. And frankly, even if they weren't incorrectly lined up, think about what that double bond looks like, right? So think about what the pi orbitals, the p orbitals in that double bond would look like. Here's one of them. Here's the other one. That doesn't work. That is terrible overlap between two p orbitals and a pi bond. And so you really can't have that pi bond. As drawn, that pi bond is kind of impossible. And we have a rule for that. This was known at the time by somebody named Brett, who formed Brett's rule, actually used the word Brett's rule in his own paper, which is a lot of ego even for a chemist. But yeah, the Brett's rule is that you can't really have a double bond at a bridgehead like that. So we really don't need to worry about elimination messing up our plans here. Okay, let's go to the paper. So they make the chlorine by a different mechanism entirely, and then when they reflux it in potassium hydroxide in ethanol, so this is hardcore base boiling water, boiling ethanol, very, very harsh conditions. Most other SN2 reactions would go very quickly under those conditions. Here, they don't see anything. They recover starting material and tar. They know what the alcohol looks like. They don't see it anywhere. And actually, the reactions were so harsh, they actually started eating the glass. So the glass got eaten up, but this material didn't. So what that tells us that no alcohol means no SN2 by some crazy front side mechanism. If we keep reading that paragraph, they're also now going to try to force an SN1 reaction. They're going to do it by a kind of a way that we haven't talked about. Silver ion is special because silver forms super, super strong ionic bonds with chloride, bromide, and iodide. You might remember this from general chemistry, KSP, that kind of stuff. And so adding silver ion is kind of a good way to rip off a halide from a carbon to kind of give yourself a carbocation, even if it's secondary. But when we add silver nitrate to the solution, we don't see anything. They use the word opalescence in this paragraph. Basically, when a little tiny bit of silver chloride forms, it's so insoluble that the material gets cloudy, a special kind of shiny cloudy, like a pearl-handled pistol or something. And so what they say is that when they run this reaction, they don't, again, refluxed in ethanol, 48 hours, they don't see any cloudiness that would indicate any silver chloride got formed. So no alcohol, just starting material, back, no silver chloride. And so what that tells you is you never formed that cation because it couldn't be planar. So this was an amazing paper. This tells us that an SN2 reaction must go with backside attack and inversion, and that the SN1 reaction really does need that carbocation to be able to be planar. Again, this was a watershed paper by Bartlett and Knox. Bartlett was a giant in the field at Harvard and was kind of recognized as such for many decades. Knox was a PhD student in his lab, and Bartlett was very laudatory and complimentary of his work, and I think most people know this paper. Most people in the field know this paper backwards and forwards. However, Knox never got a tenure track position at a big school like Harvard and Yale, where he could have a big research budget and really push this science. He only got positions at very, very small schools that had bad research budgets to do stuff. He ended up at a privately run lab for some years, was very productive there. But then when that lab failed, he went into industry, had a good career in industry, many patents, but he never had a big lab to strictly do research and to follow his muse. And I think that was a really, really big loss for the field, because I think he could have accomplished a lot. If you're wondering why nobody gave this great chemist a chance to run his own lab, it's because he was one of the first African-American chemistry PhDs in America, actually along with his brother. They were both chemistry PhDs. And this is a picture from Bates College. So Bates is in Maine. It's very, very similar to Lawrence. I know people there. So this is when he was there, so about your age. And again, while he had a good career by any standard, the field shut him out, and that hurt the field a lot. So when we focus on making sure that everybody in chemistry gets their fair chance to succeed and is included, this is why, because it hurts my field, and it hurts us as a society that we are shutting really talented people out. So that's where that motivation comes from for me.